Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll go through work 3 for the rate of reactions. This is for the combined science curriculum where the 3 natural sciences are combined into one subject. So both the Cambridge International as well as Cambridge IGCSE also offer combined science curriculum for these 14 to 16 years old. In this question, we have an experiment where the student is investigating how the rate of reaction between magnesium and acid is affected by the surface area of the solid. So here, this is what we are changing. So here we are just interested in the surface area of the solid. What we change is basically going to be what we call independent variable. So what you change is what you call independent variable. Of course, we have also learned that there are other factors that could affect rate of reaction, as you have learned from your syllabus, from the lectures in this specific playlist. So factors affecting rate. In the previous work, you have seen that concentration could affect rate of reaction. As concentration of the reactant increases, rate will go faster. You also know that temperature could affect rate of reaction. When temperature increase, your particles will have more kinetic energy and therefore they can collide faster and collide more frequently, therefore rate will also increase. We know that the use of a catalyst will speed up the rate of reaction, and we also know that surface area could affect the rate of reaction, in that when you have a bigger surface area such as a powdered form versus a lumpy or a one big piece where the surface area is a lot smaller, then the rate will be slower, rate will be smaller when you don't have a very big surface area, but rate will be faster when the surface area of the solid is much bigger. So what we're changing here is just the surface area. It means we do not want the concentration to change, we do not want the temperature to change, and we do not want the use of catalyst or the absence of catalyst to be changed at all. Basically, these 3 are what we call control variable, things we don't want to change, but they could affect the rate of reaction. What we are measuring is the rate of reaction. So this is going to be your dependent variable. You can't really measure rate, but you can calculate rate. So what we are actually measuring is the time. So time is actually your dependent variable. And you can convert time to rate because rate is going to be 1 divided by time. The longer the time taken for the reaction, the 1 divided by bigger will give you smaller rate. That means it's a slower rate of reaction. But the shorter the time it takes for that reaction, 1 divided by smaller will give you bigger value, and therefore shorter time would mean faster rate of reaction. Longer time would mean slower or smaller rate of reaction. In this reaction, we have magnesium and acid. As you know, magnesium being a metal, so if I have a metal plus acid, I will get a metal salt. This is from a year 9 syllabus, year 9 curriculum. Depending on the acid that you use, you will get different name for the salt. The salt that you get from hydrochloric acid is a chloride salt. If you use sulfuric acid, H2SO4, you will get a sulfate salt. If you use nitric acid, which is HNO3, you will get a nitrate salt. Hydrogen is a gas at room temperature and pressure. As you know from year 9 structure and bonding, these are the covalent bond between a hydrogen atom and a hydrogen atom that is just a H2 molecule. So the dot and cross consists of 1 covalent bond, 2 electrons being shared there. In this setup here, you have acid and metal, and it will produce gas. The gas will pass through the delivery tube and collect over this water, and then the gas produced will slowly fill up the space here, and it will push the water level down. And this thing have line. If you see this measuring cylinder, they have these black color lines, and that means you are allowed, and that enables you to read the volume of the gas collected. Okay. This is called a water bath there. It's just filled with distilled water. So the gas will come in and fill up this space, pushing the water level down. These are the procedure, very important. She removed the bunk. So the bunk there refers to this. This is your rubber bunk. So obviously we need to seal up this part of the tube so that the gas doesn't escape from here, because we are collecting the gas. We don't want the gas to escape from there. And of course, this thing is not immersed in here because you're producing a gas. You don't want the liquid to go in there. You just want the gas to pass through the delivery tube. And of course, this thing is immersed below the water there. The measuring cylinder is below the water, because if you lift it up above the water level, all the water is going to come down and you won't be collecting a gas at all. So what happened is she placed this 1 cm of magnesium ribbon. So this is a strip. This is called a strip, magnesium strip. So it's a strip meaning just like one line of it. In the bottom of this test tube, she measures out 10 cm cube of acid and she starts the stop clock. You might not be used to this word called stop clock. You are more than welcome to use the word stopwatch. It means the same thing as stop clock. With the time on, the stop clock reaches 10 seconds. So when it reaches 10 seconds after you start the stop clock, then she added the acid and then replaced the bung as tightly as possible. Tightly to prevent gas from escaping, to prevent the gas from escaping. You don't want the gas that you want to collect to escape at all. She stops the clock. When does she stop the clock? When the volume of the gas collected become 10 cm cube. So when the gas is collecting, this volume of water will come down as the gas fill up the space, and you stop the timer when it reaches 10 cm cube as it reads on the measuring cylinder. This is the instruction here. You stop timing when it reaches 10 cm cube there. She also remembered to subtract 10 seconds from the time display. Why is that? Because she only waited until 10 seconds before she actually added in the acid. So acid is only added after 10 seconds. Okay, that's why she subtracted the time, because before that 10 seconds there was no reaction before that. Now in this table here, we have the length of magnesium. As we are changing the length of magnesium, the magnesium strip is getting longer and longer and longer. I'm trying to show the size here, like 1 cm, 2 cm, 3 cm. So obviously the surface area increases, because the longer the strip, the more is the surface area they are in contact with the acid. So this is one way of changing surface area. So what happened with the time? We need to read the time here. So she subtract 10 seconds from the time shown on the clock. This is very, very, very important, because this shows if you can read. Can you read the instruction? Have you read the instruction? Okay, so based on this will already subtracted 10 seconds. So based on our stopwatch here, remember, subtract 10 seconds from each one. Subtract 10 seconds from each one. Here, what you read is 22.5 seconds. And you want it to the nearest second. As you could see, you don't want it to the nearest second. As you could see the table here, this is 0.5 or 0.0. So you can do the point something. So 22.5, that's going to be what you put in for the 3 cm of magnesium. 22.5 there. Number 4 here, you have 4 cm, you have 16.5 seconds. So I'm just going to write 16.5. However, I made a mistake. You know what was my mistake? My mistake was I forgot to subtract 10 seconds from each. So I need to take away 10 seconds. So minus 10 seconds. On the calculator, it will give me 12.5 seconds. That's my last answer. That's my final answer, 12.5 and not 22.5 as you see here based on the instruction here. Minus 10 seconds for the right hand side one. I get 6.5 seconds after I take away 10 seconds. Now what is this red here? Did they ask us how to fill it in? For each length of magnesium, follow the instruction. For each length of magnesium, complete column 3 by calculating the rate using the formula. So follow the question. Can you read the question or not? This is number 10, 10 divided by the time. So the rate is going to be, the rate is equal to 10 divided by the time. What I've done earlier in the question was I talk about 1 over time because there's the general relationship between rate and time. So it's just a proportion, it's inversely proportional. Sometimes question asks you to do 1 over time, but here the question specified 10 over time because that's what the question told us to do, okay, for each length. So they've given us some space here. I don't necessarily need the space. So what I do here is 10 divided by 37.5. Did they tell us how many significant figure? They did not say how many significant figure or how many decimal place, but based on the data, here this is 1 decimal place, but 1, 2, and 3 significant figure. 6.5 is 2 significant figure. 2 or 3 significant figure or 1 decimal place would be okay. 10 divided by 37.5. What I get on my calculator is 0.2667. There's too many numbers. It's impossible for you to write everything. It's not sensible. So what we do is we read 1, 2, 3 significant figure, or we can do 2 significant figure. I look at the next one. This is more than 5 or equal to 5, greater than or equal to 5. Therefore, I add 1 to the previous one. So it becomes 267. So there is 3 significant figure. The rate to 3 significant figure there. Significant figure is a primary school or a lower secondary mathematics there. For the next one, I get 10 divided by 19.0. And my calculator to 3 significant figure, it show me that 1, 2, and 3. So I look at the fourth one. This is lesser than 5. So I don't do anything to the 6 at all. On to the next one, I have 10 divided by 12.5. I get 0.8. That is what my calculator show me. If I want to be consistent to 3 significant figure, this is only 1 significant figure. So I added 2 more 0 there. 1 significant figure, 2 significant figure, 3 significant figure, lower secondary mathematics. Last one then, 10 divided by 6.5. And I get 1.538. 3 significant figure, number 1, number 2, number 3. Look at the fourth one, greater than or equal to 5. This becomes 1.54. Okay, so 1.54 there. What we could see is the rate increases. As the surface area increases, the rate of reaction increases there. How does the rate vary? Vary means change with the length of magnesium ribbon. So to answer this kind of question, you cannot just write one word. You have to talk about how. So I talk about as the length of magnesium ribbon increases. So that was from the table. As the length of magnesium ribbons increases, get higher, we saw that the rate of reaction also increases. This is just stating. They don't ask you to explain. This is basically straight from the table. Look at the data. The length increases 1 to 2 to 3 to 4, getting higher. The rate also increases, getting higher, getting higher, getting higher. Increases or get higher. Now the very last one here, since the magnesium ribbon is quite thin, doubling the length approximately doubles the surface area. Now, how does the rate vary with the surface area of the magnesium ribbon? So here they're asking you specifically on the surface area. So what we can say again is, as the length of magnesium ribbon increases, I need to relate that to surface area. Based on this information, so the surface area of magnesium also increases. So the surface area also increases. Therefore, rate increases as well. So they want the relationship between the rate and the surface area. So we can say as the surface area of the magnesium ribbon increases, rate increases as well based on this information and what we had gathered in the previous question. What is important is I must talk about surface area increasing and that will lead to lead increase, whereas the previous one is length of magnesium ribbon increase, rate would also increase there. On to the next one, the teacher said that the rate of reaction doubles. So basically it increases by 2 times when the length is double. State whether the result show. Does it show that or not? Is it correct or incorrect? That's the first bit of the question. You must show which results support your statement, whether it's correct or incorrect. Okay, let's have a look at the data. So it talk about double the length, double the rate. Well, if we look at experiment 1 and also 2, so from 1 cm to 2 cm, what happened to the rate? The rate increases, but by how many times? That's the question. By what factor? By a factor of, here is where you need to do division. Division is a primary school mathematics. So you're doubling the length. By how much does the rate double? 0.526 divided by 0.267, I get 1.97. So this give or take is approximately 2. So therefore we can say this statement is correct. So I can say the statement is correct because the statement says that when I double the length, so that means the length multiplied by 2, double the length, the rate also increases by the same factor, approximately 2 there. Okay, so you got to use the data in order to support your answer and not just say it. That's why it's 3 marks, because you got to talk about does it support or does it not. I have shown factor number 2 first, which is to do with showing the results, and then I say the statement is correct because I have already shown you based on this data that approximately translate to double the rate when you double the length of the magnesium. The next question, why does she wait 10 seconds before adding the acid? Remember earlier we took away 10 seconds from each of these reading because we did not add the acid at time equal to 0. We started the stop clock, but we only added the acid when it reaches 10 seconds. So there is a gap between starting the stopwatch and adding the acid because you also need to close the bunk. So the reason is because one hand is holding stopwatch, the other hand is adding the acid. Which hand actually help you to replace the bunk? So you can see there's a difficulty doing 3 things in one go, whereas it's important to start the stopwatch first, put it on the bench. When you read 10 seconds, one hand add the acid and the other hand close the rubber bunk straight away. So one hand add the acid in there, the other hand close the rubber bunk, because your stopwatch already started and is placed on the bench and you don't have to hold it with your third hand or whatever, and then you only start the timing at 10 seconds. So we can see that there is a difficulty. Okay, it's difficult to start timing and then adding the acid and replacing the bunk or stopper, replacing the bunk. So I'm just using the word in the instruction without adding new stuff, all at the same time. So basically we are saying that it's impossible for us to do all at the same time. It's difficult to do everything at the same time. That is why we waited until 10 seconds and then we have the stopwatch placed on the bench. When it reach 10 seconds, we start reading, we start adding in the acid and replacing that, and then we start collecting the gas, and then that's why we took away 10 seconds. We subtracted 10 seconds from each because there is to subtract the first 10 seconds, which didn't give you any reaction at all because you haven't added in the acid. Okay, on to the very last question in this work. What can the student do to test the gas? This is a metal plus acid reaction. As you have known from year 9 chemistry, metal plus acid give you hydrogen gas. So hydrogen gas diatomic molecule. So the test is basically using a burning or a lighted splint. So hydrogen, well, test for hydrogen, use a lighted splint. A lighted splint is the one where the flame is still glowing. Sorry, not glowing. You cannot use glowing because glowing is where there is no more fire, no more flame. So you got to use lighted or burning splint. And then it will burn with a pop sound. It burns with a pop sound. So the pop sound is characteristic for the test for hydrogen. The test for oxygen is using a glowing splint, and the glowing splint will relight or rekindles back into flame because oxygen support combustion. Hydrogen will burn with a pop sound. Okay. In this first question, we have a student who wants to find out how a change of temperature can affect the rate of reaction. So based on what we have learned from the lecture tutorials associated with this topic, we know that rate of reaction, is affected by a couple of factors, one of which is temperature. And when temperature increase, rate would increase as well. Reaction will go faster as well. We also know about surface area. So surface area means the point of contact between the solid and the solution in which they react with. So as the surface area increase, rate would increase as well. And then we also know about concentration. So concentration of solution. When the concentration of solution increase, red would increase as well. And last but not least, when we use a catalyst, so when we use a catalyst, if a catalyst is used, therefore the rate will be faster, and therefore you will get a faster rate of reaction as well. So here we are investigating how the change of temperature could affect the rate of reactions. So temperature, the temperature here, so temperature is going to be our independent variable, because that is what we are changing. What you change in an experiment is what you call independent variable, and what you are measuring is the rate of reactions. So what you measure actually is not the rate of reaction, but it is actually the time taken for the reaction. So you are measuring the dependent variable, which in this case is time. So in this case is time, and you can relate that to rate, because rate is somehow related to 1 over time. When you have shorter time, 1 divided by shorter time will give you a higher rate, meaning the reaction is faster if it takes shorter time. But if time is really long for the reaction, 1 divided by bigger will give you a smaller rate, meaning it's a lot slower type of reaction. In these reactions, we have ethanoic acid and a marble chip. So you might not have learned ethanoic acid at this point, but ethanoic acid is present in vinegar, but it's basically an acid. And you have marble chip, which consists of calcium carbonate. Back in year 9, you have learned calcium 2 plus and CO3 2 minus. So this is what you call carbonate. 1 carbon, 3 oxygen, and 2 minus charge. So the name is called calcium carbonate. So that was from year 9, combined science chemistry. And you have learned something called valency. Valency means you take the number on the charge. So the number on this charge is 2. The number on this charge, which is 2 minus, is just 2. And then I do cross multiply in order to get the formula. But you could simplify this further in order to give you the simplest whole number ratio. So that is basically how many of these atoms that you have actually, how many of these ions that you have actually, which is why calcium carbonate come down to Ca2 plus and CO3 2 minus. Your charge cancel out, 1 of each CaCO3. What you have learned in year 9 also is that when you have a metal carbonate, any sort of metal carbonate, when you react that with any acid, you're going to get metal salt. Depending on the acid, hydrochloric acid give you chloride, nitric acid, HNO3 give you a nitrate salt, Nitrate, and then a sulfuric acid, H2SO4 will give you a sulfate salt, and you get carbon dioxide. So carbon dioxide is 1 carbon and 2 oxygen. You also get water as your other product. This is a key type of reaction for acid plus metal carbonate. You get 3 products, the metal salt, the carbon dioxide, and the water. And it is this thing here that we are investigating, the bubbling of carbon dioxide. You get bubbles because carbon dioxide is a gas. So carbon dioxide, CO2, is a gas. We don't see the colorless gas. We are breathing out CO2. We don't see that. But we see it here in this experiment because we see bubbles. She takes the temperature of the dilute acid. As we know, you are changing the temperature here and see how that affects the time taken for this reaction to occur. And that's why you can relate time and the rate of reaction there. So what we have there is the marble chip, the carbonate, and add a bit of acid and replaces the delivery tube, basically to seal it up. So these are rubber bunk. So you need to seal it up, because if you don't seal it up here, the carbon dioxide produced, the bubbling that you see, the carbon dioxide will just escape and it wouldn't be bubbled into this thing here. So here they have used water, and we'll talk about it later on in terms of the test for carbon dioxide later on. We do not use water to test for carbon dioxide. There's a very specific test for it, okay? But in this experiment, we are just looking at how fast the reaction is going as the temperature changes. So as soon as she placed the marble chip into the test tube, which already contained, and then she added in the acid, and then she put in the delivery tube here to seal it up, then she starts the clock. She starts the clock there, referring to the stopwatch or the stop clock. So in our lab, in physics, you will have learned that you use something called a stopwatch to record time. She makes a mark in this table 5.1 every time she see a bubble coming up. A bubble meaning one bubble. So she's going to count the bubble, how many bubble comes up. She makes a mark every time there is one bubble. After 20 seconds, so after 20 seconds, she stops. Then she warms up a new sample. Warming means heating up. Heating up means temperature would increase. So that your temperature would be changing, and that is what you're changing in this experiment. As the temperature changes, how would the rate changes? Now this table 5.1 shows the number of bubbles within 20 seconds. Remember, she stopped timing after 20 seconds. At this first temperature, 18 degrees Celsius, you could see there's 1, 2, 3, 4, 5. So there are 5 bubbles in 20 seconds. We're going to count the number of bubbles here for 30 degrees Celsius. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I count 13 bubbles altogether for 30 degrees Celsius. You will have your own way. I have my highlighter, but then that's because I'm working on a screen. As you're working on a real question paper, you're not allowed a highlighter. You need to be able to do this in 1 minute. You only have 1 minute for 1 mark. Be very, very careful in a real exam. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So I've got 26 bubbles in green there altogether. And we're going to count now for the 49 one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. It seems a bit pointless for all of this, but you know, these are easy marks for you to get in 1 minute. Okay, count the number of marks there. So plot a graph of your number of bubbles. Vertical axis means up and down. So this is the y-axis. These are the vertical axis. Against the x-axis. The x-axis are the horizontal axis. So left to right temperature there. So I'll have temperature on the x-axis. Do not forget that after you write in the label, you should have the unit of which is stroke degrees Celsius, because the unit is degrees Celsius. That was from your table earlier. On my y-axis, the vertical axis, this will be the number of bubbles. Essentially, it's actually the number of bubbles in 20 seconds from the table actually. But if you write down number of bubbles, that's perfectly fine as well. But from the table, it's number of bubbles in 20 seconds from your table. We have on the x-axis 18 degrees Celsius to 49 degrees Celsius. So the most important thing is you cannot just randomly put in the value. So we have 18 degrees Celsius, our lowest, and then our highest is 49 degrees Celsius. If I say this is 0, then this is 10, then this must be 20 because this is a division of 10 small square. If this is 10, this must be another 10, which means 20, another 10 is 30, 40, and 50. They would cover all the, they will have covered all the range for the temperature on the x-axis. So 10 there, 20 there, 30 there, 40 there, and 50 there. Hopefully you can see that that is actually equally spaced out because that's what graph is all about. On the y-axis, you have 5 to 37. 5 to 37. So you need to go from 5 to 37. If you put down this as 5, then you will have this as 10. Then this one as 15, 20, and 25. And we can see that we have a problem because 37 is above 25. We run out of the space on the graph. So we cannot use 5 then. We go to the next available option, which is 10, which means if this is 10, then you have to add another 10, you get 20. The next one, add another 10 is 30, 40, and 50. They will have covered all the points. 5 is there, 37 is somewhere there below 40, so they will have covered all the points there. So this is perfectly fine as your axis there. It's all about decision making. The first point here, 18 degrees Celsius and 5 bubbles. 18 degrees Celsius is there. That is 18 degrees Celsius because that one is 10, that one is 15, 16, 17, 18. 18 and 5 bubbles. So use a cross to draw the point there, to plot the point. 18 and 5 bubble, 30 degrees Celsius and 13 bubbles. 30 degrees Celsius and then 13 bubble, 1, 2, 3. So that's 13 bubble, 10, 11, 12, 13 bubbles for 30 degrees Celsius. The next one, 42 degrees Celsius, 26 bubbles. 42 degrees Celsius is there. 26 bubble is going to be there. So 42 degrees Celsius and 26 bubble, there's 25, there's 26. Next up, you have 49 degrees Celsius and 37 bubble. 49 degrees Celsius and 37 bubbles, that is going to be there. So that is 49 there, just one small square below 50. And then 37 is 35 because it's 30 and 40, 30 and 40, 35 is there, 36, 37. Now they want us to draw a smooth curve. So they don't say it's a straight line, they say it's a curve. So what a curve means is it's not going to be a straight line, it will be a curve. So I'm trying to draw something that will, nope, I don't want to draw a straight line. Let me just try that again. So that is probably the best curve I can draw. That looks ugly actually. Perhaps that is not the best I can draw. I can draw a bit better than that. So perhaps that's the best I can draw. Okay, you might draw it better than me. For 3 marks, it's all about choosing the right scale on the x-axis, the right scale on the y-axis, the labels on the x-axis and the y-axis. Y-axis is vertical, x-axis is horizontal x-axis there. Okay, and draw the smooth curve. Now suggest why it would be difficult for this student to use a higher temperature for this experiment. As you can imagine, you're trying to determine the number of bubbles in 20 seconds. Already close to 50 degrees Celsius, you have like close to 40 bubbles in 20 seconds. Imagine if you go higher temperature again, you can imagine that you have a lot more bubbles produced in 20 seconds. It's going to be impossible to keep track and also to count the number of bubbles manually in 20 seconds because you produce too many bubbles, okay? So at much higher temperature, your reaction is going to be so much faster. Your reaction will take place at a much faster rate. Reaction becomes so fast. Reaction takes place very quickly. But why is it impossible? Why it become difficult? Okay, too many bubbles or bubbles produced very rapidly. Too many bubbles to be counted. Quite difficult to count in 20 seconds. Okay, you can imagine that it's impossible to count when you have too many bubbles when the rate is so much higher. Okay, now the next thing is basically asking you in terms of the behavior of the reacting particle. So this is kinetic particle theory. So kinetic particle theory is a year 9 topic. Basically what happened to the particles as you increase, raise mean increase the temperature, it means it goes higher. Why do you get more carbon dioxide given off? Meaning to say more bubbles, meaning more gas and therefore more carbon dioxide. This question is about why rate increase as temperature increase. This is the same as in the other work, as in the syllabus, as in the lecture tutorials. As temperature increases, we need to talk about the kinetic energy. So as temperature increases, your reacting particles, the reacting particles will gain more kinetic energy. So they gain greater amount of kinetic energy and therefore they will move faster. So they move around faster and then they will collide more frequently. So they come into contact with each other more often, so they collide more frequently. Therefore, the rate of reaction increases. And when your rate of reaction increases, we produce a lot more carbon dioxide in a fixed time. Okay, so hopefully that makes sense there. This last question is about the test for carbon dioxide. The test for carbon dioxide gas, which has this formula of CO2 from your year 9 structure and bonding. You know that carbon form 4 covalent bonds between the nonmetal and nonmetal. They share electrons. So double covalent bond means the carbon there share 2 electrons and the oxygen will share 2 electrons. Oxygen from group 6 of the periodic table, it will still have 1, 2, 3, 4 in the outer shell after you use 2 for forming covalent bond. This is very popular year 9 covalent bonding topic. Okay, now they want you only to write a word equation for what happened when you add lime water to the carbon dioxide, for which it will turn milky. So this is actually not the formation of CO2, but rather the CO2 is undergoing a reaction. But I cannot write CO2 because the question specify word equation, and I know how to write word equation. The product is actually calcium carbonate. This calcium carbonate is insoluble in water, which is why you get these insoluble white or cloudy or milky precipitate. So the presence of CO2 gas, meaning carbon dioxide, is present. It forms the insoluble. Insoluble means does not dissolve. So the insoluble white solid, or you can say milky solid, or you can say chalky solid. So they all refer to the same thing. Basically, a white solid, a chalky solid, or a milky solid that is insoluble in water. Okay, that is the calcium carbonate. And that only happened because the lime water is actually calcium hydroxide, and that will react with the CO2 to give you the insoluble calcium carbonate. Of course, we don't write calcium hydroxide here, we just write as lime water because there's a test with carbon dioxide. When it turns milky or cloudy, the lime water turns milky or cloudy because CO2 gas is present there. Okay, so that's it really for this tutorial. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry. That's at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram to get connected. I'll see you in the next tutorial video.